Alright, gang, here we go. This is for physics, unit 7, part 6, version video 2. Alright, so this is the second half, second third, last third of part 6. Alright, so we're talking about timbre, we're going to talk about beats, differences in frequency, so on and so forth. Alright, so this is pretty easy stuff here. You just got a little bit of new stuff to learn, as always. Okay, so here's the deal. Instruments themselves do not vibrate in a single mode. When we say mode, that means essentially just one harmonic. Alright, those are the same. Essentially saying the same thing. Alright, so when you play an instrument, you're actually producing not just one frequency or one harmonic, you're playing several at the same time. Alright, and so what gives different instruments different qualities of sounds or timbre, okay, is how many harmonics and how intense, remember, each of these harmonics are. Remember, intensity is this watts per meter squared. Remember this guy from before. But anyway, and they vary with different instruments. Okay, so timbre is the quality of the tone resulting from the combination of the different harmonics. Now, your fundamental frequency is what determines the pitch. Okay, so that's the note that you're playing. Okay, so if you're playing a B flat on a trombone, then you're playing your loudest harmonic. Okay, is that B flat. But then because you're playing the trombone, it has several other harmonics that are all playing at the same time, and that's actually what makes it sound like a trombone. So here we've got a little graphic here, okay? And in a tuning forks are really special because they only vibrate at one harmonic, whatever harmonic that they vibrate at, and it's all determined based on the length and the material that it's made out of. And so it vibrates at just that harmonic and no other harmonics. And so the resultant waveform of all the different harmonics that are playing for it is just a simple sine wave that just matches the wavelength and frequency for whatever harmonic that they're playing. Okay, pretty easy. Now clarinets, its harmonic series looks kind of like this. Okay, so you've got, you know, these different harmonics. So on a clarinet, you've actually, the main note you hear is the third harmonic, but you also hear these other harmonics that are below it and some harmonics that are above it. And so the resultant waveform looks something like this. Now your brain, your ear, can't hear individual harmonics coming from an instrument. It doesn't hear, oh, I hear 90% third harmonic and 10% fifth harmonic. No. Your brain hears just one wave coming in, and it constructs and deconstructs, and because they're different harmonics, they have different wavelengths and different frequencies, and so they add up together and you get different constructive and deconstructive waves all happening at the same time. And so what your ear actually hears is something closer to this here. All right, and so this is the constructive and deconstructive interference, this resultant waveform, and that's what you actually hear. And so that's why clarinets sound different than a tuning fork, even though they might be playing the same pitch. And then violas, okay, violas look even more different. You know, the first and second harmonics vibrate about at equal intensities, and then the third through, you know, sixth harmonics occur, and then not anything until the ninth. It's kind of interesting. But then the resultant waveform looks something like this. It's a lot more smooth than the clarinet, right? But it's still not nearly as consistent as the tuning fork. So anyway, so that's kind of what's going on when you listen to music, and this idea is why different instruments sound the way they do. Electric guitars, brass instruments, piano versus the organ. You know, they're all producing pitches, you know, that might be at the same frequency. Okay, but because they have different harmonics and different intensities of harmonics that are all playing at the same time, they sound like different instruments. Okay, last thing we need to talk about is this idea of beats. Okay, now if you're a musician, you've ever tried to tune your instrument, you're already familiar with this idea. We're just going to discuss very superficially like the physics behind it. Okay. So beats are caused because you have two waves that have very similar frequency, but they don't line up completely. So notice that this top one here, this top graph, we've got the red wave here, and it goes back and forth, up and down. And then you've got a blue one. Now these two guys have very, very similar wavelengths and frequencies. You know, the wavelength on the blue is just ever so slightly shorter than the red. Right here, they're completely lined up, but then when you get over here, notice that there's just this ever so slight difference, and this difference compounds itself as you move farther away from the spot where they matched up completely. And so remember, your brain can't hear individual waves. Your ear hears them all combined together. And so what your ear ends up hearing is the resultant waveform. And so that's made by all the constructive and deconstructive interference all occurring at the same time. So where these completely match up with one another, you get complete constructive interference. And notice that it's doubled its height from what it was before. And then over here, where it's completely destructive, you're completely flattened out, okay, over here on the ends. So when you actually hear this and they're slightly off one another, they actually sound like they're getting louder and then softer. They go ba. It's like pretty beautiful, right? So anyway, so here's some notes about it, okay? So they're produced by two waves that have the same intensity and slightly different frequencies. Okay, and really this is most pronounced when the frequencies are nearly the same. Obviously, when you play chords, so on and so forth, you don't really get this effect because the frequencies aren't as close together, right? And so the sound pulses from soft to loud and back and forth and back and forth. All right, and we use this to tune instruments. So if you're playing two instruments and you're trying to get two instruments to tune, okay, then you actually listen for the beats. If you can hear beats, that means you're not quite in tune. If you can't hear the beats, you're not quite. Then you're completely in tune. And so, like old school piano tuners would actually have a case of tuning forks, like, you know, dozens of tuning forks, and they'd sit there on the piano and they'd play a tuning fork, hold it up to the ear, and then play the key on the piano, and then they'd hear and they'd listen for those beats, and when the beats went away, they knew their string completely matched their tuning fork, and that means that string was in tune. And then they just slowly go through all 88 keys. Yeah, it sounds like a pain in the neck, doesn't it? Okay, now they have cool little apps and stuff like that. Makes life a lot easier. But then, all right. So that's how you tune instruments, essentially, and it's all about the constructive, deconstructive interference. Now, the interesting thing is if you can count the number of beats you hear per second, it's simply the difference in the two frequencies, okay? So if your frequencies are 1 apart, you should hear 1 beat per second. If your frequencies are 2 apart, you should hear 2 beats per second. If they're 3 apart, 3 beats per second. All right, so we're going to try something here. All right, we're going to see if we can hear what's going on with these guys. All right. So let's see. So here I've got an online tone generator, and we're going to play. So there's 440. Okay, there's an A at 440, and then here's another one at 440, and so you shouldn't hear anything different, right? So it just kind of plays these two tones and it just does its thing. Okay, and then if I take one of these and I put it one lower, all right, notice that you can now hear these two. You hear this pulse. Yeah, you hear this pulse, and it's happening 1 per second, and that's because these two guys are 1 hertz apart from one another, so they're increasing by 1 per second. And then we can take it down again, all right? And so then now it's completely doubled because now they're 2 apart, so we should hear 2 per second, okay? And then 3 per second, and then 4 per second. And we just kind of keep going from there, and then it goes away because now there's no more beats. And so that's it for part 6. Good luck. Do your practice problems. Let me know if you have any questions. Proud of you. Keep going. I'll see you on the flip side.